the frontier, looking at where we can get to next, and adding those nodes to the frontier, repeating this process over and over until either we remove a node from the frontier and it contains a goal, meaning we've solved the problem, or we run into a situation where the frontier is empty, at which point we're left with no solution. So let's actually try and take this pseudocode, put it into practice by taking a look at an example of a sample search problem. So right here, I have a sample graph. A is connected to B via this action. B is connected to nodes C and D. C is connected to E. D is connected to F. And what I'd like to do is have my AI find a path from A to E. We want to get from this initial state to this goal state. So how are we going to do that? Well, we're going to start with a frontier that contains the initial state. This is going to represent our frontier. So our frontier initially will just contain A, that initial state where we're going to begin. And now we'll repeat this process. If the frontier is empty, no solution. That's not a problem, because the frontier is not empty. So we'll remove a node from the frontier as the one to consider next. There's only one node in the frontier, so we'll go ahead and remove it from the frontier. But now A, this initial node, this is the node we're currently considering. We follow the next step. We ask ourselves, is this node the goal? No, it's not. A is not the goal. E is the goal. So we don't return the solution. So instead, we go to this last step, expand the node, and add the resulting nodes to the frontier. What does that mean? Well, it means take this state A and consider where we could get to next. And after A, what we could get to next is only B. So that's what we get when we expand A. We find B, and we add B to the frontier. And now B is in the frontier, and we repeat the process again. We say, all right, the frontier is not empty, so let's remove B from the frontier. B is now the node that we're considering. We ask ourselves, is B the goal? No, it's not. So we go ahead and expand B and add its resulting nodes to the frontier. What happens when we expand B? In other words, what nodes can we get to from B? Well, we can get to C and D. So we'll go ahead and add C and D from the frontier. And now we have two nodes in the frontier, C and D. And we repeat the process again. We remove a node from the frontier. For now, I'll do so arbitrarily just by picking C. We'll see why later, how choosing which node you remove from the frontier is actually quite an important part of the algorithm. But for now, I'll arbitrarily remove C, say it's not the goal, so we'll add E, the next one, to the frontier. Then let's say I remove E from the frontier. And now I check I'm currently looking at state E. Is it a goal state? It is, because I'm trying to find a path from A to E. So I would return the goal. And that now would be the solution, that I'm now able to return the solution, and I have found a path from A to E. So this is the general idea, the general approach of this search algorithm, to follow these steps, constantly removing nodes from the frontier until we're able to find a solution. So the next question you might reasonably ask is, what could go wrong here? What are the potential problems with an approach like this? And here's one example of a problem that could arise from this sort of approach. Imagine this same graph, same as before, with one change. The change being now, instead of just an arrow from A to B, we also have an arrow from B to A, meaning we can go in both directions. And this is true in something like the 15 puzzle, where when I slide a tile to the right, I could then slide a tile to the left to get back to the original position. I could go back and forth between A and B, and that's what these double arrows symbolize, the idea that from one state, I can get to another, and then I can get back. And that's true in many search problems. What's going to happen if I try to apply the same approach now? Well, I'll begin with A, same as before, and I'll remove A from the frontier. And then I'll consider where I can get to from A. And after A, the only place I can get to is B, so B goes into the frontier. Then I'll say, all right, let's take a look at B. That's the only thing left in the frontier. Where can I get to from B? Before, it was just C and D. But now, because of that reverse arrow, I can get to A or C or D. So all three, A, C, and D, all of those now go into the frontier. They are places I can get to from B. And now I remove one from the frontier, and maybe I'm unlucky, and maybe I pick A. And now I'm looking at A again. And I consider where can I get to from A, and from A, well, I can get to B. And now we start to see the problem, that if I'm not careful, I go from A to B, and then back to A, and then to B again. And I could be going in this infinite loop where I never make any progress because I'm constantly just going back and forth between two states that I've already seen. So what is the solution to this? We need some way to deal with this problem. And the way that we can deal with this problem is by somehow keeping track of what we've already explored. And the logic is going to be, well, if we've already explored the state, there's no reason to go back to it. Once we've explored a state, don't go back to it. Don't bother adding it to the frontier. There's no need to. So here's going to be our revised approach, a better way to approach this sort of search problem. And it's going to look very similar, just with a couple of modifications. We'll start with a frontier that contains the initial state, same as before. But now we'll start with another data structure, which will just be a set of nodes that we've already explored. So what are the states we've explored? Initially, it's empty. We have an empty explored set. And now we repeat. If the frontier is empty, no solution, same as before. We remove a node from the frontier. We check to see if it's a goal state, return the solution. None of this is any different so far. But now what we're going to do is we're going to add the node to the explored state. So if it happens to be the case that we remove a node from the frontier and it's not the goal, we'll add it to the explored set so that we know we've already explored it. We don't need to go back to it again if it happens to come up later. And then the final step, we expand the node and we add the resulting nodes to the frontier. But before we just always added the resulting nodes to the frontier, we're going to be a little cleverer about it this time. We're only going to add the nodes to the frontier if they aren't already in the frontier and if they aren't already in the explored set. So we'll check both the frontier and the explored set, make sure that the node isn't already in one of those two, and so long as it isn't, then we'll go ahead and add it to the frontier, but not otherwise. And so that revised approach is ultimately what's going to help make sure that we don't go back and forth between two nodes. Now, the one point that I've kind of glossed over here so far is this step here, removing a node from the frontier. Before, I just chose arbitrarily, like let's just remove a node, and that's it. But it turns out it's actually quite important how we decide to structure our frontier, how we add and how we remove our nodes. The frontier is a data structure, and we need to make a choice about in what order are we going to be removing elements. And one of the simplest data structures for adding and removing elements is something called a stack. And a stack is a data structure that is a last in, first out data type, which means the last thing that I add to the frontier is going to be the first thing that I remove from the frontier. So the most recent thing to go into the stack, or the frontier in this case, is going to be the node that I explore. So let's see what happens if I apply this stack-based approach to something like this problem, finding a path from A to E. What's going to happen? Well, again, we'll start with A, and we'll say, all right, let's go ahead and look at A first. And then notice this time, we've added A to the explored set. A is something we've now explored. We have this data structure that's keeping track. We then say from A, we can get to B. And all right, from B, what can we do? Well, from B, we can explore B and get to both C and D. So we added C and then D. So now, when we explore a node, we're going to treat the frontier as a stack, last in, first out. D was the last one to come in. So we'll go ahead and explore that next and say, all right, where can we get to from D? Well, we can get to F. And so, all right, we'll explore, put F into the frontier. And now, because the frontier is a stack, F is the most recent thing that's gone in this stack. So F is what we'll explore next. We'll explore F and say, all right, where can we get to from F? Well, we can't get anywhere, so nothing gets added to the frontier. So now, what was the new most recent thing added to the frontier? Well, it's now C, the only thing left in the frontier. We'll explore that, from which we can see, all right, from C we can get to E. So E goes into the frontier. And then we say, all right, let's look at E. And E is now the solution. And now we've solved the problem. So when we treat the frontier like a stack, a last in, first out data structure, that's the result we get. We go from A to B to D to F. And then we sort of backed up and went down to C and then E. And it's important to get a visual sense for how this algorithm is working. We went very deep in this search tree, so to speak, all the way until the bottom, where we hit a dead end. And then we effectively backed up and explored this other route that we didn't try before. And it's this going very deep in the search tree idea, this way the algorithm ends up working when we use a stack, that we call this version of the algorithm depth-first search. Depth-first search is the search algorithm where we always explore the deepest node in the frontier. We keep going deeper and deeper through our search tree. And then if we hit a dead end, we back up and we try something else instead. But depth-first search is just one of the possible search options that we could use. It turns out that there's another algorithm called breadth-first search, which behaves very similarly to depth-first search with one difference. Instead of always exploring the deepest node in the search tree, the way that depth-first search does, breadth-first search is always going to explore the shallowest node in the frontier. So what does that mean? Well, it means that instead of using a stack, which depth-first search, or DFS, used, where the most recent item added to the frontier is the one we'll explore next, in breadth-first search, or BFS, we'll instead use a queue, where a queue is a first in, first out data type, where the very first thing we add to the frontier is the first one we'll explore, and they effectively form a line or a queue, where the earlier you arrive in the frontier, the earlier you get explored. So what would that mean for the same exact problem, finding a path from A to E? Well, we start with A, same as before. Then we'll go ahead and have explored A and say, where can we get to from A? Well, from A, we can get to B, same as before. From B, same as before, we can get to C and D. So C and D get added to the frontier. This time, though, we added C to the frontier before D. So we'll explore C first. So C gets explored. And from C, where can we get to? Well, we can get to E. So E gets added to the frontier. But because D was explored before E, we'll look at D next. So we'll explore D and say, where can we get to from D? We can get to F. And only then will we say, all right, now we can get to E. And so what breadth first search, or BFS, did is we started here. We looked at both C and D, and then we looked at E. Effectively, we're looking at things 1 away from the initial state, then 2 away from the initial state, and only then things that are 3 away from the initial state. Unlike depth first search, which just went as deep as possible into the search tree until it hit a dead end, and then ultimately had to back up. So these now are 2 different search algorithms that we could apply in order to try and solve a problem. And let's take a look at how these would actually work in practice with something like maze solving, for example. So here's an example of a maze. These empty cells represent places where our agent can move. These darkened gray cells represent walls that the agent can't pass through. And ultimately, our agent, our AI, is going to try to find a way to get from position A to position B via some sequence of actions, where those actions are left, right, up, and down. What will depth first search do in this case? Well, depth first search will just follow one path. If it reaches a fork in the road where it has multiple different options, depth first search is just, in this case, going to choose one. It has no real preference. But it's going to keep following one until it hits a dead end. And when it hits a dead end, depth first search effectively goes back to the last decision point and tries the other path, fully exhausting this entire path. And when it realizes that, OK, the goal's not here, then it turns its attention to this path. It goes as deep as possible. When it hits a dead end, it backs up and then tries this other path, keeps going as deep as possible down one particular path. And when it realizes that that's a dead end, then it'll back up and then ultimately find its way to the goal. And maybe you got lucky and maybe you made a different choice earlier on, but ultimately this is how depth first search is going to work. It's going to keep following until it hits a dead end, and when it hits a dead end, it backs up and looks for a different solution. And so one thing you might reasonably ask is this algorithm always going to work? Will it always actually find a way to get from the initial state to the goal? And it turns out that as long as our maze is finite, as long as there are only finitely many spaces where we can travel, then yes, depth first search is going to find a solution, because eventually it'll just explore everything. If the maze happens to be infinite and there's an infinite state space, which does exist in certain types of problems, then it's a slightly different story. But as long as our maze has finitely many squares, we're going to find a solution. The next question, though, that we want to ask is it going to be a good solution? Is it the optimal solution that we can find? And the answer there is not necessarily. And let's take a look at an example of that. In this maze, for example, we're again trying to find our way from A to B. And you notice here there are multiple possible solutions. We could go this way, or we could go up in order to make our way from A to B. Now, if we're lucky, depth first search will choose this way and get to B. But there's no reason necessarily why depth first search would choose between going up or going to the right. It's sort of an arbitrary decision point, because both are going to be added to the frontier. And ultimately, if we get unlucky, depth first search might choose to explore this path first, because it's just a random choice at this point. It'll explore, 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 and it'll eventually find the goal, this particular path, when in actuality there was a better path. There was a more optimal solution that used fewer steps, assuming we're measuring the cost of a solution based on the number of steps that we need to take. So depth first search, if we're unlucky, might end up not finding the best solution when a better solution is available. So if that's DFS, depth first search, how does BFS, or breadth first search, compare? How would it work in this particular situation? Well, the algorithm is going to look very different visually in terms of how BFS explores. Because BFS looks at shallower nodes first, the idea is going to be BFS will first look at all of the nodes that are 1 away from the initial state. Look here and look here, for example, just at the 2 nodes that are immediately next to this initial state. Then it'll explore nodes that are 2 away, looking at this state and that state, for example. Then it'll explore nodes that are 3 away, this state and that state. Whereas depth-first search just picked one path and kept following it, breadth-first search, on the other hand, is taking the option of exploring all of the possible paths kind of at the same time, bouncing back between them, looking deeper and deeper at each one, but making sure to explore the shallower ones, or the ones that are closer to the initial state, earlier. So we'll keep following this pattern, looking at things that are 4 away, looking at things that are 5 away, looking at things that are 6 away, until eventually we make our way to the goal. And in this case, it's true we had to explore some states that ultimately didn't lead us anywhere, but the path that we found to the goal was the optimal path. This is the shortest way that we could get to the goal. And so what might happen then in a larger maze? Well, let's take a look at something like this and how breadth-first search is going to behave. Well, breadth-first search, again, will just keep following the states until it receives a decision point. It could go either left or right. And while DFS just picked one and kept following that until it hit a dead end, BFS, on the other hand, will explore both. It'll say, look at this node, then this node, and it'll look at this node, then that node, so on and so forth. And when it hits a decision point here, rather than pick one left or 2 right and explore that path, it'll again explore both, alternating between them, going deeper and deeper. We'll explore here, and then maybe here, and then keep going. Explore here, and slowly make our way, you can visually see, further and further out. Once we get to this decision point, we'll explore both up and down, until ultimately we make our way to the goal. And what you'll notice is, yes, breadth-first search did find our way from A to B by following this particular path, but it needed to explore a lot of states in order to do so. And so we see some trade-offs here between DFS and BFS. That in DFS, there may be some cases where there is some memory savings as compared to a breadth-first approach, where breadth-first search in this case had to